Hello everyone. Today what we do is we'll demonstrate moment distribution method through one more example. Is a frame example which undergoes side sway. So today is again a demonstration of moment distribution method. The example that we'll consider is this. Again, if you remember, in slope deflection method also we considered the similar example. Now we'll be analyzing the same example through moment distribution method, and then we'll compare the steps and the final results. Okay. Now, if you remember in slope deflection method how we considered side sway, we use the usual procedure of slope deflection method, means writing the slope deflection equation, then satisfying the equilibrium at every joint, and then in addition to that we needed one more equation, and that equation we obtained by comparing the shear force with the horizontal forces. Okay. Now we won't do the same thing here, but in some way the procedure that we follow in moment distribution method has a similarity the procedure that we use in slope deflection method for solving the same example. Okay, let us see what is that. Now you see, this problem can be divided into two sub problems. One problem is a problem which has no side sway. So the side sway is restricted, and the sway is restricted by providing a hinge, providing a support at C, which gives essentially a horizontal reaction. Now since there is no axial deformation, so providing only support at C will prevent the side sway. Okay, so the point, since the point C is not able to move in this direction and there is no axial deformation in BC, so point B will also remain at the same position. So there is no sway, not in member AB and not in member CD. Now then this is just considering this part, only the vertical load, because this vertical load will not cause sway in this structure. Okay. Now then what we do is then we allow the frame to undergo displacement in this direction. Okay, suppose this is the sway takes place at B and C, and the amount of the sway is delta. We don't know the value of delta. Okay. Now it is an iteration method, and in slope deflection method what we did is we directly use the equilibrium equation to get the equilibrium equation where we actually compared all the forces in horizontal directions. Okay. Now again it is an iterative method, moment distribution is an iterative method. What we do is we give one arbitrary sway, give some value of delta. Okay. Now we know that, see, in this problem sway takes place because of some horizontal load, right? But what is that horizontal load, we don't know. Okay, but we can derive an equation in which if we know this horizontal force we can obtain the sway, right? Now what we do here is we allow the member to sway, allow the structure to sway by some arbitrary value, and then knowing that sway deflection, sway this delta here, we determine that what is the force that may cause the frame to sway delta amount. Okay. Now we calculate this force. Okay. Now what we do is we compare this force with the reaction that we get from Cx. Okay. And then from this comparison we will determine what is the final moments, final internal forces in the member. Well, let us demonstrate that first. Okay. Now you see the first example, since there is we have two sub problems. One problem is we divided the entire problem into two parts. One is this part and another is this part. Now as far as this part is concerned, we have already analyzed this part in the previous in the last class. You remember, since the portal frame subjective to uniformly distributed load, there is no sway takes place. So but the same procedure that we have done in the last class we can continue with, then we will end up with the same results. Just to refresh your memory, if you remember, these are the slides from last class, the same example we used, and we calculated the carryover factors are half, and then corresponding absolute stiffnesses are this, and from this absolute stiffness we calculated the distribution factors for member BC and BA, and then CB and CD, and again from the distribution then the step 1, the fixed end moment we calculated for member BC, for member AB and CD fixed end moments at 0. And then once we know the fixed end moments, then we have the final this is the final iteration steps. Okay, these are the fixed end moments, and then we iteratively we applied the balancing moments. First we calculated the unbalanced moment at every joint, and then applied the balancing moments, which is equal and opposite to the unbalanced moments, and then balancing moments needs to be distributed over the members, over the connecting members, and then that distributed moments may get carried over to the other end depending on the support condition. Okay. Now, and finally we keep on doing it, finally we get the convergence or reaches the tolerance limit, and then finally this is the result that we obtain. And this is the bending moment diagram. If you remember, this is the bending moment diagram for this part. So, what we have is, we have two parts now. Actual problem is this, which is subjected to vertical distributed load and horizontal load like this. I am not writing the dimensions in this case. This is A, B, C, D. Now, this is divided into two parts. Just now as I shown, these two parts are, one part is this, is this where it is subjected to vertical loaded on BC, A, B, C, D, and then we have a support at C, which will provide horizontal reaction, and because of this horizontal reaction this will not move. Okay. But as far as the member forces are concerned at A, B, moments are concerned at A, B, C, D, they can be obtained by the same procedure, and then plus we have another part which is with the same thing, and then we give some arbitrary sway. So, and then we give some arbitrary sway. Okay, and this value is delta, this value is delta, this value is delta. Okay. Now, we'll give some value of delta, and then what we determine what is the force that might have caused, what is the force, what is this force that might have caused this kind of deformation, and then this is equal to this plus this. Now, as far as the analysis of this concern, analysis of this is exactly as the same. Okay. So, what we do now is, we won't repeat the process. For the analysis of this, you can go back to the previous class and see the different steps, but final result is this. So, for this we take the final results, and then what we do is, we will see how to analyze this part, and then once we have the solution for this part, then how to combine them to get the solution of the actual problem. Okay. Now, yesterday the problem there is a small difference between the problem that we considered yesterday and the sub problem 1. This is, say, sub problem 1, and this is sub problem 2. Okay. Now, the sub problem, as I said, as far as the internal forces moments are concerned at various joints A, B, C, D, the moments will be same, but there is a small difference between the problems that we considered in the previous class and this problem, and the difference is, now here we have a horizontal, we have a support at C. Okay, and this support will provide some horizontal reactions. Okay, but there was no horizontal reaction at C in this problem. But again as I said, as far as the moments are concerned, and if you apply moment distribution method and they follow the steps, you will see that as far as moments are concerned, this will be same, but in addition to that, there will be a horizontal reaction at Cx at C. And let us first find out what is the horizontal reaction here. Considering in order to calculate the horizontal reaction here, we take the moments that we already obtained in the last class. Okay. Now, how do we proceed? First, we first take the free body diagram of this part. What would be the free body diagram of this part? This is C, this is D, and then we have a moment like this here, and then a moment like this moment here, and then in addition to that, what we have is this end is supported fixed end. So, there will be a reaction force, and suppose the reaction is Ax. Okay. So, this moment is MBA and this moment is MAB, means moment at A in member AB, and this is moment at B in member BA. Okay. And then we will also have a shear force here. So, suppose that is equal to V. Okay. That is equal to V. So, there is no other forces in this member. Okay. Now, this is A, this is A, and this is B. And if you remember, in slope deflection method also we calculate the horizontal forces in sway problem. Okay. And how we calculate the horizontal forces? By considering the free body diagram of these two members. Okay. Now, what we do is we apply the equilibrium condition at B, and what it says that equilibrium condition at B will be summation of MB is equal to 0. And what are the forces will contribute? Ax will contribute, this will contribute, and this will contribute. And what are the forces values we have? Again, you see the values are at A it is 25 clockwise, at B it is 50. So, these two are clockwise moment. Now, then it will be positive, and then this will be if you write the values, we get Ax is equal to MAB plus MBA divided by LAB. LAB was 5 meter, this is 5 meter, this is 5 meter. So, if you substitute, then Ax will be MAB is 25.1 plus MBA is 50 and divided by LAB is 5, and we get 75 kilonewton. So, this is Ax. Okay. This is Ax, and similarly, if we take the free body diagram of this part, free body diagram of CD, and what would be the free body diagram of CD? Free body diagram of CD will be this, and then there is a moment here which is MCD, and then another moment here which is MDC, then vertical, then horizontal reaction which is dx, and then another force V, shear force V. You take moment about this, and what is the moment? Here it is minus 25, here it is minus 50. So, here it is minus 25. Okay. These are minus, not plus. This is minus 25 and this is minus 50, and if you substitute that, and this length is 5 meter once again, and we get dx is equal to again minus dx is equal to minus 75 kilonewton. Okay. Dx is equal to minus 75 kilonewton. Okay. Now, this is the problem. Okay. Now, so what happens is, then what would be the reaction at C? Reaction at C will be, okay, there is one thing, you please correct it. The first problem will be like this. This is 10 kilonewton. 10 kilonewton. The first problem is like this, and this will cause sway in this this might have caused sway in this structure, but the sway is restricted by this horizontal force. Okay, and then the second sub problem is you allow the sway, you allow some arbitrary delta amount of sway in this problem. So this is sub problem 1, this is sub problem 2. Okay. So in sub problem 1 we have horizontal force, and that the sway due to this horizontal force is restricted by this support, but this horizontal force will not change the moment because it is acting, this force is acting at the joint. So it will not contribute anything to the moments at the joints. Okay. Therefore, for this problem you get the same moments. Okay. Now, so we have horizontal force Ax is equal to 75, dx is equal to minus 75. Now, let us find out what is the reaction, Cx, what is the reaction Cx here. Okay. Now, reaction Cx here will be, then you apply the equilibrium condition will be again here itself we can do that equilibrium condition will be summation of fx is equal to 0, and what are the forces we have in fx? We have force in a reaction at Ax, then reaction Ax, reaction dx, and then horizontal load 10 kilonewton, and then reaction Cx which is in this direction, reaction Cx which is in reaction Cx. Okay. Now, if we apply all this, what we get is we get Cx is equal to 10 kilonewton. Cx is equal to 10 kilonewton. Now, actually without doing all this, without taking these parts separately also, we could have obtained the Cx by drawing the free body diagram of the entire structure and take moment about this. Let us do that. If we draw the free body diagram of the entire structure, okay, which is subjected to this load and then this load, then in addition to that we have moment here and we have moment here, and then reaction here also, vertical reaction, horizontal reaction and horizontal reaction. This is Ay, Ax, it is MAB, and this is dy, dx, and this is MDC. Now, and then we have horizontal reaction here Cx. Okay. Now, instead of taking the free body diagram of these parts separately, we can take the free body, we can take the moment about this, and these dx and ax will not contribute, and the contribution will be from Ay, from MAB, from DC, from this load and from this load, and then Cx, and you can compute the Cx. But again, for that Cx you need to find out what is the value of Ay. Okay. Now, so this is up to you how you find out the support reaction, which part you take and which free body diagram you take, and apply the equilibrium condition. It is, there are many way you can do this, but the main point is we need to find out what is the support reaction, and support reaction is we have obtained a Cx is equal to 10 kilonewton. Okay. So this is the solution for the first sub problem. Now, let us now solve the second sub problem. And this, what is the second sub problem? Second sub problem is this. Second sub problem is we take this is the second sub problem. Just now I showed you. Let us draw it once again. There is. Okay, so this is delta, this is, and this is, they are delta. Okay, they are delta. So there is a sway delta amount. Now, again this we solve using moment distribution method. And what is the first step in moment distribution method? We know first step is to find out the absolute stiffnesses, then distribution factor. But since we are talking about the absolute stiffness and distribution factor, they depend on the geometry of the geometry and material property of the structure. So, since the geometry and material properties are same, distribution factors, carryover factors, some support conditions are also same. Distribution factors, carryover factors, all will remain same. So, whatever distribution factor and carryover factors we calculated, the same thing we can use here. Now, the next step is to find out what is the fixed end moments. In the previous example, in this case, the fixed end moments we had because of this external load. Okay. Now, this load will not cause any fixed end moment because it is applied on the fixed end, only on the support on the joint itself. Now, but this joint displacement, this you can view as a settlement of joint B, and this can be treated as a settlement of joint C. So, this settlement of joints will cause fixed end moments, and we have already seen if the joint undergoes settlement, then what is the value of fixed end moment. So, what is the value of fixed end moments? Fixed end moments are fixed end moments MAB fixed end moments is equal to MBA which is again fixed end. If you consider this joint, this member, and in this member this joint undergoes displacement settlement of delta amount, and both the cases if you remember, the fixed end moments will be minus 6 EI delta by LAB. This is the fixed end moment, and if you and this is the fixed end moment. Now, similarly, what would the fixed end moment for this the fixed end moment will be MCD of F fixed end moment is equal to MDC, again fixed end moment, is equal to minus 6 EI delta by LCD. Okay. The fixed end moments in fixed end moment in BC, there will be no fixed end moment in BC. The fixed end moments only we have in member AB and member CD. Now, delta is unknown here, isn't it? We don't know how much this way takes place. Now, what we do is we will give some amount of sway, some arbitrary amount of sway. Let us assume, let delta is equal to, give delta is equal to 100 by EI. Okay. 100 by EI is a very arbitrary value. You could have taken, you may take 10 by EI, 1 by EI, or any arbitrary value. By EI, the reason of taking EI here, because then this EI and this EI will cancel each other. So, we won't be having any EI in the expression. Okay. So, if we take 100 EI as delta, then fixed end moments becomes these become minus 120 kilonewton meter, and this also become minus 120 kilonewton meter. Okay. So, fixed end moment at A, at B, at C, and at D will be minus 120 kilonewton meter for members AB and members CD. Okay. Now, once we have the fixed end moments, rest is to do the iterations. Now, let us do the iteration. The iterations in moment distribution method, the same thing we have to do. So, first is let us take we have 3 members, the same procedure will follow. Suppose this is A, and okay, and draw a line. This is the table for moment distribution method, and okay. Now, this is B when B belongs to AB, and this is B when B belongs to BC, and this is C, this is C, this is D. And then we have distribution factor. Distribution factors here it is 2 by 3. It is 1 by 3. You can check the previous class where we have obtained this distribution factor, and this is 2 by 3. right. These are the distribution factors at B and C. Now, what is the fixed end? First step is to write the fixed end moments. The fixed end moments, here it is minus 120 and here it is again minus 120, here it is 0, for BC it is 0 and it is minus 120 and again it is minus 120. Okay. So, this is fixed end moment, fixed end moment. Now, once we have the fixed end moment, next part is we need to check what is the status, equilibrium status at every joint. Now, at joint B, what happens? There is no it is not in equilibrium. So, there is an unbalanced moment of minus 120 and again joint C there is an unbalanced moment of minus 120. So, in order to balance it, we have to apply a moment, fictitious moment of 120 at joint B and 120 of joint C. And once we apply, that moment is called balancing moment, and when you apply the balancing moment at the joint, then that balancing moment will get distributed in the connecting members as per the distribution factor. So, what happens at joint B? At joint B, we need to apply a load, we need to apply a moment of 120 kilonewton. At joint C also we need to apply moment of 120 kilonewton. Then these minus 120 and these 120, they will balance each other, and minus 120 120 they will balance each other. These 120 will get distributed in BA and BC, and the contribution of BA will be 2/3 of 120, 2/3 of 120. 120 and contribution in BA will be 120, 1/3 of 120. Similarly, here, and this will be 80 and this will be 40. So, contribution will be, this will be 80 and this will be 40. Similarly, this will be 40 and this will be 80. Okay. Now, this is the balancing, this is the distributed balancing moment. This is distributed balancing moment, right. Now, once you have the distributed balancing moment, then this moment, there will be a carryover moment at A because of the moment at B, there will be a carryover moment at D because of the moment at C, and from B to C and from C to C. And carryover factors, we have calculated carryover factors are half here. So, the 80, so the moment 40 will be carried over to A. This is how we show the carryover moment, and then similarly from 80 it is 40 here, and from 40 it is 20 here, from 40 it is 20 here. And these are all carryover moments. These are all carryover moment. Okay. Now, once we have the carryover moment, and then again we need to check the status of equilibrium. Now, let us see what is the status of equilibrium. At B there is an unbalanced moment of 20, and at C also there is an unbalanced moment of 20. We need to apply minus 20 at B and minus 20 at C, and this minus 20 will get distributed as per this. So, if we need to apply minus 20 here, and then we need to apply minus 20 here, and once the 20 get distributed, 2/3 of 20 will be here and 1/3 of 20 will be here. So, those values are minus 13.33, this is for BA, and minus 6.67 for at B, and similarly it is minus 6.67 and this is minus 13.33. Now, this will this is the distributed balancing moment. So, this is carryover moment, this is distributed balancing moment. Now, this moment will also be carried over to here, half is the carryover factor. So, half of this will go here, minus 6.67 will go here, and then minus 3.34 will go here, minus 3.34 will go here, and minus 6.67 will go here, and this is the carried over moment. Okay. Carry over moment, and again we need to check the status of equilibrium. We need to apply plus 3.34 here, plus 3.34 here, balancing moment which will get distributed, and the corresponding distribution will be 2.22 and 1.11. It is 1.11, 2 and this is balancing, distributed balancing moment, distributed balancing moment. Again that will be carried over and this becomes 1.11 will carry over, from here it is 1.11 will carry over and from here it is 0.56 and 0.56 will carry over. So, this is carryover fact, this is carryover moment, these are all carried over moment. Okay. Now, again once we have the carryover moment, again check the equilibrium status. So, this is carryover moment, Once again check the equilibrium status, we need to, this is unbalanced moment of 0.56, we need to apply minus 0.56 here and that will get distributed among according to the distribution factor, and those corresponding value will be minus 0.37 and minus 0.19 and this will be minus 0.19 and minus 0.37 and okay, and this is the balancing moment, distributed balancing moment, distributed balancing moment. You always put a remarks column at the end where you can write the what is the steps that you have the corresponding line you have performed. Now, again there will be a balance, there will be carryover moment is minus 0.19 and then this is this from there it is minus 0.1 minus 0.1 and then it is minus 0.19. We are approaching towards the convergence. These the values are becoming very smaller and smaller, and then let us see the last step. You need to should always be the balancing the balancing moment, the distributed balancing moment, otherwise there will always be an unbalanced moment at the joints. Okay. So, these 0.1 we need to apply 0.1 balancing moment, that will get distributed and the distribution is 0.03 here and 0.07 here and it is 0.07 here, 0.03 here. So, this is the last step. This step is the carryover moment and this is distributed balancing moment. So, let us make this is the last step, because the values are very small. You can continue 0.07 is the unbalanced moment, then again you can apply some similar 0.0 minus you can know, but then you can carry this, you can get the carryover moment and then check what is the again further you can continue till you get the value 0, but it is reasonably smaller value we have obtained compared to the fixed end moment we started with. So, final results are now minus 85.75 and then it is minus 51.45, it is 51.45 and then it is also 51.45 and then minus 51.45 and minus 85.75 and this is your final. Okay. Now, you check this is also in equilibrium, this is in equilibrium. So, this is my final results. Final results for which this is the final, these are the moments at various joints when delta is equal to for delta is equal to 100 by EI, right. For delta is equal to 100 by EI, but delta we do not know, that is an arbitrary value, right. Delta may not be 100 by EI. Now, how to get the final value? Okay. Now, you see the final value will be, let us now find out for the same problem, let us now find out what is the support reactions. For the same problem, we have now obtained what is the moment. This is A, B, C, D. Okay. We know what are the moments in this. We know what are the moments. These are the corresponding moments. So, we know what is this moment. This moment is minus 80.575. This moment is minus 51, and then we have this moment. These moments all are shown clockwise, and we have this moment. Okay. Now, we can take separately this. Apply the equilibrium. We can take separately AB. the free body diagram of AB will be like this, and then this there will be it is AX, and then AY, there will be V here, and then you take free body, you get moment about this axis, moment about this point, and this will not contribute, we can get the AX. Similarly, if we do the free body diagram of CD, exactly the way we have done for the previous the sub problem 1, we can calculate what is the value of AX and what is the value of DX, and then what we do now is say AX is equal to, we get AX is equal to minus 27.44 and DX is equal to minus 27.44. Okay. Now, you see, it means what? Now, AX is equal to AX in this, AX is equal to this, and the DX is equal to this, right, and total force in this direction is AX plus DX, means this because of this delta, okay, in this moment is calculated, these moments are calculated based on all these steps we have done. These are based on the sway of amount delta. But actually what? Actually there is some force that may cause this amount of sway, right? Then what will be the force which may cause this amount of sway? The force will be this plus this. So, suppose this is the force that might have caused this delta, and this F will be, then this F will satisfy the equilibrium condition for equilibrium with AX and DX, and that equilibrium condition will be F plus AX plus DX is equal to 0, and from there we will get F is equal to 54.88 kilonewton. Okay. So, if we apply 54.80, so instead of, there are two things, instead of applying delta, the amount of sway, delta by 100, 100 by EI, sway at B and C, if we apply 54.88 at C, they both have the same effect, isn't it? So, the delta sway is caused due to this amount of force, this delta by the 100 by EI sway that we started with, that is caused because of this amount of force. Instead of 100 by EI, if you take 50 by EI, 25 by EI or 330 by EI, then you get different F value, but that F value will be consistent with the delta that you take. Now, we are almost at the final stage. Now, what we have here? We have what we have obtained in this is our first sub problem, this is the second sub problem, but if we add them, that should give the same, that should give this value. Okay. Now, it is again very simple. Instead of 100 by EI, you could have given unit displacement, unit sway here. Okay, and get what is the F value. Now, but actual reaction will be Cx, right? Actual reaction, see, these 100 kilonewton force will cause this sway, 100 kilonewton force in the actual structure, but that sway is restricted by this reaction Cx. So, essentially if we remove this reaction, then sway is allowed, right? So, the sway is actually taking place because of this 100 kilonewton force. Now, the amount of sway we assume is 100 by EI, and that sway is due to 54 by 88 kilonewton force. Means if we apply 54.88 kilonewton force, if we in the actual structure, if we apply 54.88 kilonewton load, then what will happen? Then we get a moment. Then we get a moment of the sub moment. Then we get a moment which is equal to the moment in sub problem 1 plus. Okay, let us write it. So, actual moment in sub problem 1 will be, then M original will be M sub problem subproblem 1 plus m subproblem 2 divided by f. Divided by f means this is when you apply unit force here. When you apply unit force here. Okay. Now, if we the moments that you get, that is because of the force F. And if we apply unit force, this will be the total moment, but actual reactions you have into Cx. Okay. So, total moment in original will be moment subproblem 1 plus moment in subproblem 2 by f into x. It is very similar to your apply unit load and get the corresponding moment. So, these values we have already obtained. These values are this, and for subproblem 2 the values are this. We substitute that, and for and f is equal to, we have obtained f is equal to 54.88, and we also obtained Cx is equal to 10 kilonewton, and if we substitute this, the values that we get is this. Let us finally draw the bending moment diagram and write the value. Okay. You get the bending moment diagram like this. And this is the final bending moment diagram that you get. In the previous case it was symmetric, but now it won't be symmetric. Okay. The values are, you get, this is 9.375, this is 40.625, this is again this is a 59.35, and this is 40.625. This will be the bending moment diagram, corresponding bending moment. Okay. So, essentially if you have a sway problem, then that needs to be divided by two parts. One is the structure without sway, and the structure where only sway takes place, and that because of the say whatever moments you have, that need to be calculated, and then that moment need to be normalized based on the reaction that you get in subproblem 1, and then finally you add the moments in subproblem 1 and plus the normalized reaction in subproblem 2 to get the original the moments in the original structure. Okay. Again, the steps will be clear if you do some examples. There are again many examples given in the book. Please do that, because without doing them the steps will not be clear. You may have some confusion even after all this discussion, but believe me, those confusion will be clear once you start actually applying the concept to several problems. Okay. We'll end here. We'll end here today. So, what we do next week is we'll discuss direct stiffness method. As I said that next week will be the last week of this course, and direct stiffness method, that's, as I said in the beginning, this is a very basic structural analysis course. It's the first course in structural analysis, and you will be having an advanced course on structural analysis in a subsequent semester. And the last week when we talk about direct stiffness method, that will be the transition between your the first course on structural analysis and advanced structural analysis course. Okay. See you the next week. Thank you.